Right. I will explain about the experimental procedure. There are test A and test B in this experiment. For for test A, there are several steps we need to follow. The first one is assemble test frame was placed on a workbench. Window of the test frame was made sure it's easily accessible. There are 4 securing nuts in the top member of the frame. It was like to approximately the position shown in figure 8.5. The next step is with the right hand end of the experiment resting on the bottom member of the test frame, the left hand support was fit to the top member of the frame. The support was pushed on the frame to ensure that the internal bars are sitting on the frame squarely. The right hand support was lifted into a position and the 2 remaining thumb screws was located in the securing nut. The support was pushed on the frame to ensure that the internal bar are sitting on the frame squarely. Position the support horizontally so that the rolling pivot is in the middle of its travel. So the thumb screw was tightened. The digital force display was made sure is on. The mini DIN lead from force input 1 on the digital force display to the socket mark force output on the left hand support of the experiment. The lead was ensured does not touch the beam. After that, we carefully zero the force meter using the dial on the left hand beam on the experiment. Apply a small load gently with a finger to the center of the beam and release. Zero the meter again if necessary. The step was repeated to ensure the meter returns to zero. This experiment examines how shear force varies with the increasing point load. Then the digital force display meter reached zero with no load was checked. A hanger with a mass 100 gram was placed to the left of the card, which is 4 mm away. The digital force display reading in the table was recorded. This step was repeated using mass 200 gram, 300 gram and 500 gram. Then the mass was converted into a load in Newton. Next, for test B, there are several steps that we need to follow as well. The first one is we need to check digital force display meter read 0 with no load. The beam was loaded with the hanger in the position shown in figure 8.6 by using the load indicated in table 8.1. After we get the result, we record the digital force display reading. The support reaction, which is RA and RB, was calculated and the theoretical shear force was calculated at the card. Procedure was repeated with the beam loaded as in figure 8.7 and 8.8.
For experiment theory, beams are defined as structure member support loads at various points along the member. Transverse loading of beam are classified as concentrated load or distributed load. One of the main concerns that should be put into consideration when designing beam for strength is how the material and the cross section of a beam of a given selected span should be selected if the beam is not to fail under a given loading. Applied loads in internal force consisting of a shear force of the shear stress distribution and a bending moment from normal stress distribution. For prismatic beam, that is straight beam with a uniform cross section, their design depends primarily upon the determination of the largest value of the bending moment and the shear force created in a beam by a given loading. The determination of this value and the critical section of beam in which they occur is greatly facilitated by drawing a shear force diagram and bending moment diagram. The variation of the shear force V and the bending moment M along the beam may be investigated from this diagram. The value of V and M at various points may be obtained either by drawing FPD of successive portions of the beam or from the relationship that involves the applied load, shear force, and bending moment. Determination of maximum normal stress and maximum shearing stress require identification of maximum shear force and bending moment. Shear force and bending moment at a point are determined by passing through a section through the beam and applying an equilibrium analysis on the beam portion on either side of the section.
So from the experiment, about the observation we can see the force measured by the force display increase with increased load. So in the table, only the figure 8.6 have the negative shear force. So from the graph, we got the between load and shear force. Load is on x-axis and shear force in y-axis, but this graph is actually comparison between the experimental shear force and theoretical shear force. This comparison show that there is a slightly difference between the experiment shear force and theoretical shear force. So actually different is an experiment values, as they don't show the linear relationship between the load and shear force. So this error is due to many reasons like personal error, due to experienced worker or fault apparatus.
For the calculation part, for the experiment one, we must calculate the theoretical shear force, which is the formula F given. Shear force is equal to the load times to the distance from the reaction A and the cut-off point, and divided by the length of the beam. So we go to the first load, which is W equal to 0.98 meter. So we just substitute the W into the formula, which is SC equal to 0.98. The A is 0.26 and divided by the length of the beam, which is 0.44. We get the answer 0.58 meter. So the step will be same for the other loop. For experiment 2, we need to calculate the reaction at A and B. So first of all, we must draw the three-body diagram of the figure, which is first figure, which is 8.6. So we start on the process and the direction. So of course we must use the summation of and then we cut. In this case, we can choose the one or upward to be the first value. So I choose upward to be the first value. So we cut RE plus RB is equal to 3.9. Then we apply the we can choose either point A or B. In this case, I choose the summation over either A is equal to 0, and we can choose either we want to the clockwise to be positive value or anti-clockwise. We can choose anti-clockwise to be positive value, and then we get the 3.92 right to the 0.14 plus RB right to the 0.442 and equal to 0. So in this case, RB we get negative 1.5. So we substitute the reaction B point value to this formula. RB plus and then we get the reaction at A is equal to 1.107. So this step will be same for the figures 8.7 and 8.8. For the experiment 2, we also need to calculate the theoretical shear force, which is we consider the right side of the or the left side of the cut of beam. So I consider the left side to be the calculation for the theoretical force. Okay, then first we draw the figure diagram and list down all the forces and reaction, and then we apply the summation F1 is equal to 0, and then we get V plus 5.1 equal to 3.9. Then we get the shift force is equal to negative 1.25. So this value is same if we consider again the right side, which is V is equal to the R. So the step will be same for the figure 8.7 and 8.8.
I will explain about our discussion. So the question is comment of the shape of the graph. What does it tells out about the shear force where they to increase load? Does the equation we use accurately predict the behavior of the beam? So my comment is from the graph, the value of shear force increase with the load that has placed the increase. So the gradient of the shear force also increase due to increased load. The value that we got from equation determine of the size of pin, so it's accurate predicting the behavior of the pin. The question 2 is comment on how the result of the experiment compare with those calculated using the theoretical. So my comment about this result, the result of the experiment we get if the value from the experiment is less than the value of the theoretical. Less than experiment is less than from the theoretical.
In conclusion, we are able to determine the how shearing force varies with an increasing load, and this was also seen how shear force varies at the cut position of beam for various loading condition. It can be concluded that when the load placed at the beam will be increased, the shear force also increase. The digital indicator is too sensitive when we take the reading. The screen shows reading not consistently, that it could be affected by the wind or vibration at the surrounding. So here are our recommendation, which is firstly we must learn the procedure and instruction of the experiment to make sure that the experiment is run easily and smoothly. And when calibrating or set up the experiment, place a hanger with a load carefully to avoid misreading or reading or error on reading, as we know that digital force display meter is too sensitive. And make sure the apparatus is done the maintenance scheduling or up to date to avoid incident, injury or error when doing the experiment.
In my opinion, overall, all members in the group have shown their responsibility in order to complete this lab experiment. Thank you.
Terima kasih.